Hi, recording is rolling. It is Wednesday, February 1st. And let's just do some demos and a activity today, what I got lined up for you guys. And before you leave class today, I'll get you guys your next take-home quiz. We'll have it due Monday. Of course, if you finish up before the weekend, you can always turn it in early and not have to worry about it over the weekend. So that's what we're doing. Doing demos, activity. You guys get to cut and glue, and then I'll get you guys your take-home quiz before you walk out the door. Okay. So I know the past couple days we've been going hard on these puzzles. Let's just call those concluded right there. So the only ones we hadn't hit were chapter 9 with interference and diffraction. So if you're really curious about this, then you could like navigate these formulas and answer these questions. There's like a double slit experiment going on here. That's going to show up in the future when we get to quantum mechanics, and I really want to talk about it then. Right. But you guys see a poster up here that says interference on it. You guys see interference pattern. So just know, like here, you got sorry, it's back here now. Okay. If you got a couple of slits, right, and you put like a wave through, then you get two waves. There's constructive interference and destructive interference. Periodically, you get like an interference pattern. All right. So we're done with these. You guys can turn in the puzzles whenever you want. I'll have those two along with the quiz on Monday, so that if you want to use those to help you out on your quiz, because the questions are pretty similar. Okay, and let's do these demo type questions. So first, I've got a few questions for you guys involving mirrors. Right, mirrors. I pulled these out of Paul Hewitt book. So let's say we got this lady standing in front of a dresser mirror, and she's trying to see this flower on her head. Now, the premise here is that maybe she can't see the direct reflection of the flower because the flower is like too far in the back of her head. So you just kind of go with it, right? Right? Okay, draw the flower a little bit more on the back of her head. Imagine that, right? So she's also holding a handheld mirror. And what she's doing is she's seeing the reflection of the flower, right? And the question is, how far back behind the dresser mirror? So if you start here and go backwards, does she see the reflection of the flower on the back of her head? Okay. So give you guys a little time to think about that. While you gotta think about that, I'm gonna sketch it up a little bit bigger on a piece of paper on screen. And you guys see some multiple choice options there.
Behind the mirror. That's not even can.
All right, so got the explanation part drawn up here. Let's see, show of hands what you guys are thinking. How many of you guys think the answer is A, 1 meter? We're gonna say it's B, 1.5 meters. Who says it's C, 2 meters? And who says it's D, 3 meters? So it looked like the most number of hands was the most votes was on C, 2 meters. Right? That is correct. Yeah. So it's C. But so let me walk you guys through stuff like that. You want to see this? Okay. So here's same lady with a very long arm. How about that? Right here, here's the flower right here. Right. So what else to do? You may have thought about it one of a few different ways, but I'll take you guys one through it. Let's start from the flower and say like, what happens to the first reflection of the flower? So inside this handheld mirror, wouldn't it appear to be equidistant on the other side here, which would be like 0.5 meter over behind the handheld mirror? So it'd be like 0.5 meters that way. That would be true, right? Okay. So there's the initial reflection. Okay. You could do a ray diagram the whole deal, but be similar to Paul Hewitt's with the candle. Okay. And then in the dresser mirror, seeing the reflection of that reflection, and that distance is that's a 2 meter distance right there. So the reflection of the reflection is going to show up also 2 meters on the other side. So this will be there is also 2 meters. Okay. All right, so you guys go ahead.
The puzzles that you just talking about, we don't do the rest of them, correct?
Yeah, don't worry about chapter 19.
Okay.
Yeah. So just the ones we did in class is fine. Okay. And if you were absent or you missed any of those that we did in class, then of course they're all posted on Google Classroom. Okay. Ooh, this next question I like a lot. It says, here, zoom in where you guys can see this. Okay, so this guy's standing in front of a dresser mirror that's about equal to his height. It's maybe he's 6 feet tall. The dresser mirror is also pretty close to that. Okay. And he wants to see his entire reflection. Now, of course, he can't see his entire self there. But what if you started like shaving off the top and bottom of the mirror? Like, what's the minimum size of the mirror that we need to also see his entire reflection? Like, if you had a little handheld, then that wouldn't be enough. Right? The dresser mirror should be enough, right? But what's like the minimum amount? Right? You guys got these multiple choice options. Have we talked about this one yet? Oh, okay, I didn't think so. All right. So you guys see some multiple choice there. Right, so what's the minimum amount of mirror? Now, as you guys think about this, one of the catches is going to be you do have to have the mirror position in exactly the right position, right? If you have like the minimum amount of mirror, like if you have like way up here, that's no good, right? All right, so let me see, show hands. How many guys think the answer is A, a quarter of his height? How many guys think it's B, half of his height? Who thinks it's C, 3/4 of his height? And who thinks it's D, he has to be same height as him for him to see himself? And who says it's E? It depends on how far away he is. Oh, okay. So it looks like E got the most number of votes. Here, before I just give you guys the answer, let me redraw that and go through a ray diagram type approach. So have the dresser mirror. Right, that's like a flat plane, right? Okay. Now, I'm going to draw this guy like. How about some arbitrary distance from the mirror? Okay, some arbitrary distance. So like here, for example. So okay, so we can see. Could have made him closer, could have made him further away, but we'll just do the specific one. Right, so here's like ground level right here. Right, and he should see himself like same size, equidistant on the other side, right? So it should be like here's the image of himself, should be, right? Done plenty of these, right? And you're brushing your teeth in the morning, you see yourself in the mirror, right? That's what you always see, right? Same size, equidistant on the opposite side. Right? Pretty close. Right? Now let's see from his point of view, give him an eye here, reflection and eye too. So here's like object, image. Okay, right? Right. And as he's looking in the mirror, he can see the top of his head, he can see the bottom of his feet. As long as you see top of his head, bottom of his feet, you can see his entire self. Right? So let's draw those rays. So from his eyeball to looking at the top of his head, see this, okay, well, I see a light ray coming from like that direction. Okay. And so it looks like there's right at the very top of his head. Now, you guys know that ray actually bounced the Boyne law of reflection, came from like this direction. Right? There was a light ray that bounce up, skirted the top of his head like that, boing. Right here, if I drew a normal line, it would like exactly split that angle in half, the normal line, right? Okay. So that's right about there. All right, and he also looks down. He sees the bottom of his feet. So he's looking down here. Right, sees okay. Well, my feet's like down here, okay. And that's coming from a light ray, like from this direction, right? Which actually bounced off the flat surface coming from like back here. Okay. So everything's solid is the way the light rays are actually bouncing around, and then those dashed lines is like if you extrapolate backwards to the image, like oh, it looks like it came from back there. Okay, guess what? Okay. Do you guys see the actual bit of mirror he needs is this bit right here? This bit right here. Right. Let's make some measurements for like this case. So what is the height of this guy? I made this guy about 7 centimeters tall, so h equals 7 centimeters. Okay. And what's the height of this mirror bit? This is 3.5 centimeters. This right here to here is 3.5 centimeters. Ooh, you guys see how that's half of that? Okay. And if you can do like an animation in your head, it turns out that if he gets closer to or further away, I just drew him at some arbitrary distance away. Let's see what exactly I have. I have them like about 8 centimeters away. Right? But I could have made it any distance, and that would always be true. And you can try this yourself. One place I was able to do this myself was I went to I was inside an airport. It was at night. They had glass walls, and you guys know if it's nighttime on the opposite side of the glass wall, it's a really nice reflective surface, right? And I was standing up kind of close to that surface, that mirror surface, and said, okay, where's the top of my head? Where's the bottom of my feet? And made like a mental mark, like, okay, so that part in glass and that part of glass, maybe it's like a smudge of the glass or something. So there, I can see my entire self, right? And then backed up further and further away, and where the top of my head was and the bottom of my feet did not change position, right? So I could put this guy in a different position, it would still be like this bit of mirror right here. Of course, again, the catch is like you have to have the mirror like exactly at the location. If you put the mirror like down here, you can't see its entire self. Okay. But yeah, you can see your entire self with a mirror that's half your height. So if you're 6 feet tall, you need 3 feet of mirror. Okay. Okay, so this next question, to see more of her head in the mirror. Let's say you got one of these handheld mirrors, right, and you're trying to see your entire face. Now let's just deal with the flat side, not the concave side that's going to blow your face, but just the flat side. Right? So yeah, I can't see my entire face. So you hold it further away from yourself, or you hold it closer. Okay? So to see more of her face, what should she do? Should she hold it closer? Should she hold it further away, or does she just need a bigger mirror? What do you guys think? Well, we just kind of walk through this, right? Okay. Like this guy, if he wants to see his entire self, he just needs a mirror that's half of his height. Like once he has a mirror half his height, he can see his entire self. Right? It doesn't matter how close or far away he stands. Right? So if you got that, then the answer's got to be C. She just needs a bigger mirror. Okay? And you can try this yourself. Take care. I can pass this one around. Now make sure you're looking at the flat side for this to work. So you have to look at the flat side, not the concave side, but the flat side. Okay? See like how much of my face do I see? And hold it further and further away, and you'll see the exact same proportion of your face. I'll pass it around. You guys can try it yourselves. Okay, there's one more. So just for completion. Usually everybody gets this one. Okay. So you guys see a photographer here, take a picture of her friend on the bridge. Okay. And then say, well, only one of these pictures down here is the actual photograph. So which one is it, A or B? You guys are all saying, yeah, which one? B. Yeah, B, right? Right. You guys all see B? All right. So option A, they just like mirror the image like top down, but option B is like more realistic because maybe she's elevated a little bit. She can't see the underside of the bridge, but she should be able to see the reflection of the underside. So yeah, option B. Okay. So here's some mirror puzzles. Put those away. Okay, next on the list. Spectroscopy. Yeah. Anyway, I got lots of different kinds of physics classes. This week I tried to go in 3 different ways, and I think I got my notes straight, but now I keep doubting myself. So I'm have I talked about this? Have I talked about this with you guys? Okay. So yeah, let's do this. I don't think I have it. Yeah, my note said I did. So, wait, what? You guys see the line over there, the poster over there? It says spectral lines. Right? It's got like the first 8 elements. Right? So it turns out that every single element will absorb or reflect back a certain wavelength of light. And now this is Paul Hewitt's book, so this is conceptual physics. I think your textbook has a similar one. Now they give examples for, it says according to this, hydrogen, sodium, and mercury. Right? And this is just the visible part of the spectrum, right? Going from like red to violet, right? Okay, so what is this useful for? Well, a few things. One thing is that astronomers can point this at like distant stars and figure out the composition of stars, right? That's one way to say, hey, that star is like mostly hydrogen and a good amount of helium, and then like trace amounts of other things. Oh, it's like 9% oxygen or something, right? How would they know that? Oh, well, they know because of the spectral lines that the light that's coming off each of the stars, right? They can also get light refracting through atmospheres of distant planets. Have you guys ever read a science article? It's like, hey, scientists or astronomers discovered a distant planet that's it's rich with water, has lots of water on it. How the heck would they ever know that? Well, they know that because there's light that's refracting through the atmosphere of that planet that's showing lots of hydrogen and oxygen in a 2-to-1 ratio, right? Like a bunch of this and also the oxygen on that poster thing, right? You say, oh, okay, well, H2O, that's a lot of water. It's a lot of water vapor in that atmosphere. We know that's a water-rich planet. Another thing you can do with this is that if astronomers look at distant galaxies, usually these lines are actually shifted a little bit, and they're more often than not shifted to the left, like towards the red bit. Did I talk about red shifting, blue shifting? Okay, so we have talked about that. Yeah, so galaxies are moving away from each other. Think about a Doppler shift. my notes here, see if I see. Yeah, that will stretch out the wavelengths closer to the red end of the spectrum. So it's called redshifting. Okay. And if galaxies are headed towards each other, like Andromeda Galaxy is going to crash with the Milky Way one day. Here we go. Okay. So we got like red shifting and then blue shifting. Like Andromeda Galaxy is going to crash with the Milky Way. That's going to shorten wavelengths, make it more blue. And so you can use that to figure out like how fast galaxies are moving away from us. And it turns out the further away they are, the faster they're moving. It has to do with like cosmological expansion. Right? So something about how the universe expands. Right? There's no such thing as the center of the universe, or you could say the center of the universe is kind of everywhere. How the universe expands uniformly. Okay? How do you get these spectral lines? Okay? So you get these spectral lines using a tool called a spectroscope. Right? There's like a nice high, the lab version of it there. Now I have a cheap version of here, spectroscope. So if you look through this eyepiece and you point this at one of these fluorescent lights at the ceiling, it will break the that white light into colors. I'll pass this around. This is kind of a cheap version of a spectroscope. You guys can try that too. I've got a few more on my demo table, so I'll check. Right. Iridescence I want to talk about. Let me flip my screen over here. Not here. Not that. That's it's another class. I guess about that too. But right. So, yeah, thank you. Right, so, you guys ever notice? Well, another example is like a iridescence that I'm going to talk about is CDs. You guys ever look at a CD-ROM and it looks all like rainbow colors, right? So it's kind of like a silverish color, but then move it in the light, you get all these like rainbow colors off it, right? Or if you look at like butterfly wings, are kind of like shiny. Or you guys ever seen like kind of related ideas, like a puddle of gasoline? It looks all like rainbow. This is a little bit different, but kind of related idea. Right? So iridescence. Now, if you took like a butterfly wing and you like crushed it up, then like this blue butterfly would probably not be blue anymore. It's like, well, where'd it go? Shouldn't it be blue because it's like there's like blue pigment, like a blue surface? And actually, it's not blue because of that reason. It's like the shiny blue because like down at the microscopic level, it has these ridges that are about 1 micrometer apart. 1 micrometer is on the same order of magnitude as like visible light. You guys know visible light goes, where is it? I've got it right here. Like 380 nanometers to 750 nanometers. That's what your eye can detect and interpret as color. Okay. So whatever light is bouncing off of that surface is going to give wavelengths that correspond to, like in this case, like blue light. It's not because of blue pigmentation. So that's cool to know about. All right, I did want to show you guys. Okay, give you guys a crash course on this TED Talk. There's this TED Talk was a few years back that really blew my mind when I saw this. It's called femto camera. If you want to see the whole thing, so you're saying, oh yeah, back in the 1960s, they were able to get like slow motion videos, like a bullet passing. Right? Okay, and then what's he done in the meantime? So they got this new camera. It talks about how they put together and what they can do is technologically. They can actually follow a bullet of light. Right. So this is just amazing to watch. So here, let's watch this thing. Here's light in slow motion. So they had a bullet of light. There's some really fancy tricks to make this camera work, but if you want to watch the whole thing, it's called femto camera. It's slowed down by a factor of 10 billion. Like I said. Yeah, that is what a bullet of light looks like traveling across the screen. Einstein would have been fascinated by this for a reason. I mean, one of the things that led Einstein to cracking relativity was he was thinking about this question, like, what would it be like to like follow like a bullet of light across the screen? So anyway, that is really cool there. Yeah, I'll show you guys a little bit more of this. Flash closer to the end. One thing they've done with this is they said, well, if there's like an image around a corner, like you guys see that like doll behind the corner, right? It's scattering light in all directions, and that light is bouncing off, and then some of those photons are captured by this camera, right? And apply an algorithm to put the photons back together, and you can get actually like a surprisingly realistic idea of like what's invisible around the corner, just how the photons are bouncing around. So here's the model that they were able to here you go. Here's the model they were able to do just from photons bouncing off walls. So it's very cool there. I want to show you guys about pinhole cameras. So light rays want to go in straight directions, right? What if you have like a closed box and you just cut like a tiny hole in it. Well, each of those rays of light just wants to go in a straight line. So what they do in this video, just pull up YouTube, is they go into a motel room. This is over in San Francisco. Throw up a sheet there, and then blacken out the window. So they're gonna make it completely dark. They turn off the lights and it's like pitch black inside. Right? And they start cutting holes. Now over this video, they change the size of the hole. So they start with like 4 centimeters diameter. Okay. And now each of those rays of light from the outside world, there's the outside world. You guys see skyscrapers, San Francisco, right? Wants to travel in a straight line. There's the image on the back wall. And notice it's upside down, which of course it would be, because anything like from the sky is gonna go in a straight line down to the bottom of the room. Anything like from the sidewalk outside is gonna go in a straight line like to the ceiling of the room, right? So it's all like inverted, right? Everything's inverted. Now, as they change, oh look, now we got 3 centimeters diameter. As they make the hole smaller and smaller, then they're gonna get an image that's crisper and crisper. Look at that. Right? Now it looks even better, right? But the downside is that you get less light. It's like a trade-off, right? So you need a longer camera exposure to get that picture. Right? Speaking of cameras, this is how the first cameras were created. If you go back to like the 19th century, you see like pictures of like Abraham Lincoln, like, oh, here's a photograph. Right? They were these boxes that were these pinhole cameras. And then on the back, it just had film to record the image that came through. But that's how they originally got first photographs. Yeah. All right, I think that's, oh, whoops, let me do that. Let's be back over here. Those are the demos I wanted to show you guys. Actually, here. Let's do, all right, so I'm doing this activity with another class, but I have them here. Make this like perspective art. Have you guys ever seen this like chalk art out on sidewalks, where if you're at a particular perspective, like the perspective of the camera, it looks like 3D. It looks like pandas in it, right? Do all those panda heads from our point of view look about the same size, I think? But if you're actually out on the sidewalk, which takes up more space and more chalk on the sidewalk, the one closer to us, the one further in the back? Yeah, the one further in the back takes up a lot more sidewalk and a lot more chalk, right? But here it looks 3D, so kind of hard to tell otherwise, but logically that would be the case, right? So this is all from one particular artist, Nicholas Arndt, I think. See right there. Okay. The different versions of this. Okay. So what's the kind of a class version of this? Okay. So my other class, again, just want to be familiar with like, here's how you would do that. Okay. If you have a piece of perspective paper, you just like draw a picture, okay? And then you go to an actual graph paper, okay? And then you can match like point for point. You can make a 3D like that. Let me show you guys some examples. So I have like this perspective paper. I drew this tennis ball and plotted a bunch of points and then mapped that to like this Cartesian grid. Now from this helicopter point of view, of course, it looks all like warped and wonky, right? But if I shift this, right, and get it just the right angle, it should look like a tennis ball that pops out. Let me do it for the camera at home first. So if you're at home, watching this on video, because I've got 2 different videos on 2 different cameras, okay? Then that should look like a tennis ball pop out of the page right there. Right? And now if you're in class, let me turn this to get the right perspective. You see like it looks like a tennis ball? Pow. Right? That's the perspective you want, right? So that. Okay. Then okay. It's another student example. So Ian Fox, if you know, drew a little drum there, right? And then translate all the points here. Of course, here it looks all warped. If I turn this, here, I'll do the same thing. So everybody at home watching the video first, looks about like there, bam. And everybody in class, bam. Now it pops out 3D. You see that? All right, so that's there. That's pretty cool. Now, what I'm gonna have you guys do actually is put the screen over here. A different activity. Okay, we got just enough time for this because that one takes a little bit of time thinking. We get it's this one right here. And so see how it looks like the T-Rex is like following you around. So as the camera moves, looks like it's following you. Okay. Now it's not moving, it's just a completely still like cardboard cutout. Okay. No, this is a really powerful illusion though. And there. Now this is like most of the way through the video. So this is the first time they break the illusion. You guys see how the face was actually concave rather than convex. So your brain always wants to interpret faces as convex. Like it's actually concave, so it creates a solution, right? Now this I have for you guys, right? We've got just enough time to do this. So I'm gonna give you guys the template to make this. You guys got some scissors and glue on your desk. Okay. And then as long as you're making it, then I will give you guys some points in the grade book. So here's the template, right? Everybody gets one of these. Just cut them out. You guys see like some tabs. You guys see some tabs. Okay. So the brown down here, throw some glue on the tabs and make like a nice little box that you can sit on, so you can just like prop them up. Right. Then over here, you throw some glue here and here. And remember, importantly, for this to work, you want to make his face concave, right? And it works all right, like in person, but it works really well if you break out your camera phone and start taking a video and do like in the video where you saw like change of perspective, right? It looks like he's like following you around. Okay, so I'll give this to you guys, and that. Oh, one more thing, I need to get you guys your take-home quiz. That's it. I'll get you guys this and your take-home quiz. Your take-home quiz is going to be due on Monday. Of course, you can always turn it in early if you like. Okay, so that's the last 2 things today. I'll give you guys grades for those things.